Okay, I guess it's time to resume our workshop. So in the next, Ziyuan is going to give an introduction of the OCRTOC Challenge 2021. Ziyuan, can you start?
Okay, good. So, hey everyone, I'm Ziyuan Liu from Alibaba AI Labs. On behalf of the OCRTOC team, I will give you an introduction about OCRTOC, a cloud-based competition and benchmark for robotic grasping and manipulation. So regarding performance benchmarking in the field of robotic grasping and manipulation, we face some challenges. First, different researchers usually use different hardware to do research. We have a lot of manufacturers for both manipulators and end effectors. And it is quite hard to separate the algorithm performance from hardware efficiency. And it is even harder to compare algorithm performance between different researchers. On the other hand, robot hardware is quite expensive, so not everyone can afford it, and a complete robot platform, including robot arm, end effector, sensors, and the computing device, can easily cost $40,000, and this is a natural entrance barrier for this field. Imagine a newcomer with limited funding will really have issues entering this field. So to solve this problem, we proposed OCRTOC, a cloud-based benchmark for robot grasping and manipulation. The basic idea is that each individual researcher can develop algorithms on their own local machine, and maybe with the help of simulators, they can experiment it also on their machine. And after that, they can upload their algorithms into the OCRTOC benchmark. So here we focus on the rearrangement tasks, specifically table organization, so which is an essential ability for service robots. And we use standardized hardware and software system and standardized tasks with randomized objects and scenes to do algorithm evaluation on both simulator and real robots. So the key idea here is to use the same hardware setup and the same tasks to evaluate algorithms from different researchers so that the comparison can be done in a proper and fair way. And our goal is then to facilitate reproducible and generalizable robotics research and lower the barrier as well. And a task in the OCRTOC benchmark includes objects, the initial configuration, and the target configuration. So if we take a look at this example in simulation, so the task of the robot would be to rearrange all these objects so that the initial configuration transforms into the target configuration after the operation. And here we see another example for real robot. Here, the robot needs to set up the tableware so that after the operation, all this tableware is properly set up for, let's say, dining purposes. And for performance evaluation, we calculate for each object a 3D distance error using their target pose and their actual pose. So, and this error is set to an upper error bound if the object is not grasped or the distance error is greater than the upper error bound. And the performance of a solution is then the average distance error of all objects in all tasks. And here we see a general pipeline on how we do the 60 pose estimation. So basically, we render for each object a lot of templates in different viewpoints. And then from the input image, we get the object ROI, and then we do the pose estimation in the following steps: compute correspondence, outlier rejection, pose hypothesis, find the best initial pose, and then pose refinement. So as you can see, this is a quite traditional method, but it works quite robust. So to realize all the ideas just mentioned before, we need a stable software system, which is the OCRTOC software package. And it is available on GitHub, and the code link will be provided on our homepage later on. So we use Docker-based development. So Docker is a OS level virtualization technology that makes software development independent of the underlying operation system. And here in the OCR Docker image, we pre-installed several layers such as the Ubuntu layer, ROS layer, simulators, and so on. And the OCRTOC code realization contains 3 parts. In the device part, hardware drivers and simulator-related functionalities are provided, and in the standard API, interfaces to software services are provided, such as camera, grapper, transform, and so on. And in application part, our assets include non-programmable software artifacts, including such as object models and tasks. And OCRTOC sample code demonstrates how the contestant solution is called by the OCR software package. And in the contestant-related functionalities, there is mainly the evaluation module that we will also use in the online testing part. And in the contestant solution, so the contestant can also add a customized Docker layer as needed. And in the end, the contestant solution is callable by an OCRTOC interface. And we use ROS as the communication backbone. So here, the OCRTOC software package is what we as organizer provide. And based on this package, a contestant can build their own solution. And with the 2 parts together, there will be a complete OCRTOC solution, which can be evaluated in the OCRTOC benchmark. So in our OCRTOC benchmark, we have 150 object instances with their object models, triangle mesh models with texture information. And we selected 34 objects from the YCB dataset, and then we scanned 116 objects by ourselves using a 3D scanning device. So these objects can be divided into 5 groups and 36 categories. And currently we support 2 simulators, which are Sapien and PyBullet. So in the simulation, we use scene graphs to generate scenes. So here we see an example. The arrow just indicates some on top of a relationship between the object. And given this scene graph, we then sample objects from the database, and then we also add a pose to the objects. After some validity check, valid scene is then generated in the simulator. So using this OCRTOC benchmark, we held the first competition in conjunction with ICRA's 2020, and 59 teams from 12 countries have taken part in this competition. And this competition had 2 stages, which were simulation stage and the real robot stage. And in the end, the top 3 teams were granted an award. So here we see the used hardware platform. So basically we used for this competition the robot arm from Universal Robot. It's a UR5E, and a grapper from Robotic 2F85. And the used visual sensors were a Kinect DK and a RealSense D435i. So here on the left, we see the simulation tasks that we use to evaluate the algorithm. On the left, we see the initial scenes of each task, and on the right, we see the target scenes. So as you can see, we group the tasks into different difficulty levels. It goes from 1 to 5. And as the number goes up, the difficulty also increases. And on the right side, we can see the result for the simulation stage. In all, 14 teams qualified for the real robot stage, and their performance ranged from 29 centimeters to 32 centimeters. So, so as I mentioned before, this is the per object average distance error. And here we see the 5 tasks that we used for the real robot contest. So in task 1, we started with 5 objects and with a clear view on that. So it was really a simple task. So in each image, in the upper left corner, we see the target configuration. And in task 2, so it got a little bit more complicated because the target pose of some objects are already preoccupied by other objects. To solve such kind of task, you need a kind of planning to plan the motion correctly in a proper order. And starting from task 3, we add more objects to the scene. So here we had 10 objects. And then the difficulty went up in task 4 and 5 by adding more clutter and more complex scenes to it. For example, objects were stacked together, and that was really quite difficult to solve. And here from this table, we see the result for the real robot contest in 2020. So we can start from the left side. So the performance is given again in the average distance error per object and in centimeters this time. And it is compared with the baseline performance. And the baseline performance refers in this case to the case that nothing was done in the task and we directly calculate the distance error between the initial scene and the target scene. So as we can see, the final performance of the top 5 team ranged between 31% improvement to 6% improvement. And if we take a look at the graph's success rate, it was quite interesting. The best team achieved a graph success rate of 78%. They did 33 trials and 26 of that succeeded. And if we take a look at this row, so as the difficulty went up, so the improvement declined from 40% to 6% in task 5. And the blue color indicates the best performance in each task. We can also clearly see that for task 1, team number 2 achieved a 61% improvement. And in task 5, team number 1 achieved 16% improvement, but still it was the best one in task 5. And here we have a direct intuition, so what the best performance of each task could perform. So starting from task 1, I mean, this was a quite easy task. So rearranging 5 objects with a clear view on that, and the target pose of each object was not preoccupied by other objects. So in this case, we can see that 4 objects were almost correctly rearranged. So if we speed it up a little bit. Yeah, and this is task number 2. And as I mentioned, so here it got a little bit more complicated because such kind of target pose was already preoccupied by other object. And this solution needed actually a kind of planning module to plan the motion sequences properly. But as we can see here, it was not the case. And starting from level 3, we added more objects to the scene. So here we have 10, and it really started to get messy. Yeah, and from task 4, it got even more chaotic. So I would say the task stayed as a whole unsolved. So the robot arm just randomly grasped something and put that to somewhere, and not considering whether the place is already occupied or not. So, and in task 5, it was quite a nightmare, I would say, for the contestants. It was very, very difficult to solve. Okay, from both the intuition that we just got from the video and the numbers we have just seen from the table, we could say that rearrangement is still a challenging task to solve for robot. And the performance of the best team from last year was still not that good. It was only 31% improvement against baseline. And as we saw in the videos, so for better performance, we need actually at least better pose estimation, better grasping, better planning, and even more. And we have also learned some lessons from the last competition. First, baseline solution is quite needed so that the teams do not start from scratch. So a lot of teams really struggle to complete a solution by themselves. And second, trajectory planning with 6 DOF manipulators can sometimes be difficult. And real-world training data were also quite essential in order for the robot to work in the real-world application. And in the end, we noticed that a more flexible way of participation is also desired. So based on the feedbacks and experience that we gathered from the last competition, we improved the benchmark, and we will launch another competition in 2021. This is our homepage, OCRTOC.org. So first, the first thing we did is that we will provide a baseline solution. So from last year, only the blue part, it was provided by us, and the green part should be provided by the contestant. But this year, we will provide a baseline solution that contains 2 parts. First, a planning part that uses a high-level motion planning method based on the PDDL method. And the second part is the perception module, so which contains an end-to-end point cloud-based grasp pose generation method that comes from the GraspNet baseline. And we have also 2 60 pose estimation methods implemented here. So, and the way how you could submit your solution is various. First, if you use the perception part, keep the perception part of the baseline solution and only modify the planning part, and then your solution will be evaluated in the planning track. And in meanwhile, the result will also be presented in the main track. And on the contrary, if you keep the planning part and use your own perception part, and then your solution will be evaluated in the perception track, and in the meanwhile, the result will also be presented in the main track. But if you think you have better ideas and better algorithms, you can even completely do a new solution. Then your solution will be evaluated directly in the main track. And the competition format is like this. So officially, the OCRTOC 2021 will start on the 1st of July 2021, and the submission deadline is tentatively the end of November. And this year we will have 2 parallel branches, which are the real robot branch. For this branch, we allow 1 submission per month per team, and the other branch is the simulation branch. For this branch, we allow 2 submissions per month per team. And then each branch contains the 3 tracks that I just mentioned on the last slide. And for award winning, we will also grant a awards this year, but only the results in the main track will be used for award winning. And now we will come to the final details of what kind of tasks will be used for which branch. So for the real robot branch, the contest tasks will be divided in 3 sets. So first, you will have a training set with simulation support, which means that we will give the one-to-one copy of the real task simulated, and this set can be downloaded to your local machine. You can try and experiment on that. And the second set is the feedback set with video recording, which means that we do not give you the simulation task for that. However, after we will record the whole procedure during the evaluation, and after each submission, we will give you the visual feedback. And the third set is a hidden set, which means that you will never know what kind of tasks are in that. It stays a black box to the contestants. But however, these tasks are similar to the ones in the training set and the feedback set. And in the end, the award will be given like this. After the submission deadline, the top 8 teams will be evaluated again using new tasks. And in the end, the top 3 teams in the final rank will get awarded. And in the simulation branch, we predefined 150 tasks, and we will release 50 tasks to the contestants for offline training, and we will use the other 100 tasks for online testing. And for award winning is quite simple. You only need to be the top 3 teams. Okay, we will also upgrade the tasks. So this year we will have 4 scenarios, which are the kitchen scenario, the dining scenario, the workshop scenario, and the office scenario. So the reason why we updated the task this year is that we want to use tasks that are more aligned with our daily life use cases. And we will also update the robot hardware. So the major change is the manipulator. This year we will use Panda from Frank and Mika with 7DUF, and also the end effector would be the Panda's gripper with prolonged fingertips. So the other hardware device will stay the same as last year. And this year we will also provide labeled real-world data. So we will use 33 objects, and we will provide triangle mesh models for the object. And in all, we will provide 76 scenes. All these scenes contain multiple objects in that, and the per scene object 16 poses are labeled. And each scene is captured in 79 view angles, and in total there are 6,004 RGBD images, and in total we have around 30,000 per frame poses labeled in the data set. Okay, here so here we see all the contributors to the OCRTOC benchmark. So it's a huge collaboration between different various research institutes, including Simon Fraser University, University of South Florida, UCSD, WPI, DLR, Shanghai Jiao Tong University, and Alibaba AI Labs. So without the contributors, the OCRTOC benchmark has not been possible. Okay, and then by this slide, I would like to end my presentation. If you are interested in participation, please contact us at info@ocrtoc.org. Thank you for your listening.
Okay, thank you, Ziyuan, for the introduction.